Welcome to Lecture 2 of Week 4. Today we will be discussing proof techniques and strategies for demonstrating that a sequence converges. We will also be giving some number of examples illustrating the methods. As I mentioned last time, we are following pretty closely the textbook. This lecture overlaps with pages 39 through 44. Let us get started. We begin with a quick discussion of how to prove a sequence converges. First, some strategy. What do you do if you have a hunch that a sequence converges and want to prove it so? The first step is to identify the limit. You can use calculus knowledge or intuition to do this. Normally, if you have a hunch that a sequence should converge, you probably already did this part, even if subconsciously. The second step is to, of course, prove that your proposed limit is actually the limit. How do we do that? Let's look at a statement for convergence again. It is a for all there exists for all statement. Remember that a proof of any for all followed by there exists statement is like a challenge. Math is going to challenge you by giving you an arbitrary epsilon. Your job is to respond to it by telling math how you are going to find this capital N. So your task essentially boils down to, first, devise a method for finding an N from the given epsilon. Second, prove that for the N you have chosen, every later index will make the condition true. A few remarks are in order. First, what do I mean by devise a method to find capital N? This generally requires applying the Archimedean property together with some computations. How you apply the Archimedean property, on the other hand, has to factor in your eventual second step. These two steps are not really independent and should be worked at together. But if you're stuck at solving the problem, one reasonable way is to do a little bit of trial and error. Try a way of coming up with a capital N. Try to prove that any later index satisfies the condition. If it doesn't work, adjust your method of coming up with capital N using what you learned when you try to prove the condition. A very important second point that I see a lot of students hung up on is the proof process just requires you to demonstrate one N for a given epsilon. It does not ask for the best or smallest possible N that will do the trick. In fact, if there is at least one N that works, then there will be infinitely many others that will work. The way the statement is phrased is such that if N satisfies the statement, then any index P that is bigger than N will also satisfy the statement. So don't be stuck on trying to solve the inequality exactly. You can just take N as large as it takes to make whatever computations you need to do convenient. I want to spend a few minutes talking about how we know the Archimedean property plays an important role in proving convergence. The idea of proving convergence is to demonstrate that if you wait low enough, eventually the sequence will come as close as you want to the limit and stay there. This means that you are looking for a large enough natural number N, the time you need to wait. And for the statements we have available in our toolbox, the one that is most suggestive of this is the Archimedean property. Its statement literally ends in there exists a natural number N such that N is bigger than something. Now, let us start with some easy examples to see how proofs go. We start very simple, with the sequence whose terms are x sub n equals 1 over n. We first guessed the limit. Since as n increases, we expect 1 over n to decrease, we guess that the limit is 0. Our goal is to find a capital N such that the inequality, the absolute value of the difference between the terms of the sequence and the limit, is less than epsilon, holds. So we start by making clear what we need to prove. We write the desired condition by plugging in the formula for x sub n. We find that what we need to prove in order to conclude the sequence converges to 0 is that the difference of 1 over n and 0, being 1 over n, is less than epsilon. To achieve this goal, we will apply the Archimedean property. Given the specified epsilon that is positive, the Archimedean property guarantees some capital N such that 1 over capital N is less than epsilon. If we choose any small n that is even bigger, then its reciprocal is going to be smaller. From this, we conclude that if capital N is chosen as in step 3 through the Archimedean property, then for any larger lowercase n, the condition 1 over n is less than epsilon holds. Since in step 2, we saw that this is exactly what we need to prove, this means we're done. Let's do another example. This time, x sub n is equal to 1 over n squared plus 1. We start again by stating what we need to prove, that 1 over n squared plus 1 is less than epsilon. Once we achieve this, we are done. Using the Archimedean property, we can find capital N such that 1 over capital N is less than epsilon. If small n is later than big N, then 1 over lowercase n is also less than epsilon. Next, we notice that 1 over n squared plus 1 is less than 1 over n squared by virtue of having a larger denominator. This, in turn, is less than or equal to 1 over n, since, for natural numbers, 1 over n is no more than 1. So this chain of inequality leads us to the conclusion that 1 over n squared plus 1 is less than epsilon, provided that n is bigger than capital N, which was chosen in accordance to the Archimedean property against the given positive epsilon. Putting everything together, we finish our proof. In the previous example, the terms being 1 over n, which looks exactly like what the Archimedean property gives us, we didn't have to argue much once the Archimedean property was applied. In this example, we have to include some further computations to go from the application of the Archimedean property on step 3 through some reasoning involving inequalities between rational numbers in step 5 to reach the desired conclusion in step 6. In general, for proving convergence of a sequence with an explicitly given formula for its terms, these sorts of manipulation will be required. Let's look at one more example to illustrate this. This time, we will study x sub n being the reciprocal of the cube root of n. As before, we intuitively guess that the limit should be 0. To prove that the sequence converges, we then need to prove that 1 over the cube root of n is less than epsilon. So we follow the same procedure to apply the Archimedean property to get a capital N whose reciprocal is less than epsilon, from which we conclude the same is true for any greater index small n. The next step, where we do the manipulation, however, we run into a bit of a problem. The cube root of n is generally smaller than n, so its reciprocal is larger than 1 over n. This means that what we have done is not good enough to show convergence. What do? Noticing that essentially the problem is that we didn't choose n large enough, we revisit our proof and rearrange the order of how we do things. Instead of first using the Archimedean property and then doing algebraic manipulations, this time let us try to do the manipulations first. We first conclude that in order to prove that the reciprocal of the cube root of n is less than epsilon, it is enough to show that n is less than the cube root of epsilon, or the cube of epsilon. Now we can apply the Archimedean property to epsilon cubed, which, when epsilon is a small positive number, think something like 1 over 1 trillion, is a much smaller number. So when we now apply the Archimedean property, the output, which we still call capital N, is in fact much bigger than the capital N that we chose in the previous slide. By using this bigger capital N, we are able to finish our argument. Since 1 over capital N is less than epsilon cubed, for larger indices, 1 over small n is also less than epsilon cubed. But since this is what we set out to prove, that given any epsilon, we can find a capital N such that for any later index satisfies 1 over n is less than epsilon cubed, we can conclude that the sequence converges. Let's finish this lecture by doing a more involved example. This time, x sub n is equal to the quantity 3n plus 1 divided by 7n minus 4. Our first step is still to guess. Looking at the sequence, we ask ourselves what the terms look like when n is large. When n is huge, 3n is much greater than 1, and 7n is much greater than 4. So the terms that appear in the fraction without the n factor are negligible. So throwing them away, we get something that looks like 3n divided by 7n. Canceling out the n, we end up with the expected limit being 3/7. We again do some preliminary computations. First, we want to write down the thing that we need to prove. We need to control the difference between x sub n and the proposed limit, 3/7. So let's plug in first what x sub n is, and then do some arithmetic, and we find that x sub n minus 3/7 is equal to 19 over 49n minus 28. Notice that for natural numbers n, 49n is at least 49 and bigger than 28, so the resulting fraction is always positive. This means that the absolute value of the difference is just the difference itself. So, the desired conclusion that the absolute value of the difference is less than epsilon is the same as requiring the fraction 19 over 49n minus 28 is less than epsilon. It helps to bring this to a form a little easier to manipulate later. So we do some algebra and solve the inequality for n, finding that the inequality is the same as requiring n to be at least 1 over 49 times the quantity 19 over epsilon plus 8. Notice that this complicated looking expression is always positive. The given epsilon is positive by assumption of the statement that we hope to prove. So 19 over it is positive. Adding 28 and dividing by 49 doesn't change the sign of the term. Our goal on this slide is to simplify the targeted expression into something easier to manipulate. And in this form, the application of the Archimedean property almost suggests itself. To finish the proof, since this complicated expression starting 1 over 49 is positive, as one demonstrates on the previous slide, we can apply to it the Archimedean property, which asserts that there is some natural number capital N that is bigger than this number. Now, if small n is even bigger, then it would also be bigger than this number. But as that is what we need to prove in the first place, we are done. So, what's the moral of the story? To prove that a sequence converges to a limit, we need to prove a statement that says, given any epsilon positive, we can find a natural number n such that the sum condition holds. The step in which we actually construct the natural number n, how it connects to the given epsilon, is always through the Archimedean property. The connection is not always direct, since the desired conclusion will suggest manipulations so that the application of the Archimedean property is more direct in giving the desired index n. Okay, that's it for this lecture. Do your exercises and practice this process. I will see you next time.